Okay, so we have a way to actually calculate the work done by a gas, and the work done by a gas is P delta V. But this only works if you're at constant pressure. Okay? So remember, our work is in joules. Okay? And a joule is a Newton meter. All right. And then our pressure, if we use our SI units, is in pascals. And remember, pascals is newtons per square meter. And then our volume is in cubic meters. And so if you look at that, then you see that it works out in standardized units. If we use pascals for our pressure and cubic meters for our volume, then it works out that we end up with joules, which is Newton meters. Okay. Also remember, though, that 1 cubic meter is 1,000 liters, and 1 kilopascal is 1,000 pascals. So, if we take and use kilopascals and liters, do you see this works out? This is 1,000 pascals times 0.001 liters, because if we rearrange this, 1 liter is then 0.001 cubic meters. So this will also work out if you use kilopascals and liters as well as pascals and cubic meters. So this is our general definition for work done by a gas. Okay? And if the pressure or if the volume expanded, remember, if the gas got bigger, if the volume got bigger, then we had positive work because the work was done by the gas. The gas actually pushed against the surroundings so that it could expand. So it pushed on the surroundings. And so the force and our distance, if we really looked at work, force and distance, it's pushing on the surroundings and it went the same direction. So that's going to give us a positive value for our work. That's kind of how that positive negative thing works in terms of work itself. So we have the equation, P delta V, but that only works when we have constant pressure. So what do we do if we don't have constant pressure? Sometimes what we can do is we can create what's called a PV diagram. We can look at how the pressure changes with volume. Okay, so if we end up, let's say we started here at state A, and we expanded our gas, or we actually didn't expand it, we just increased the pressure and went to B, and then we went to C, and then came back to A. That's called a cyclic process because you go through a cycle. Do you see how you went through a cycle? And you got back to the same spot. Well, your internal energy at any spot is 3/2 PV. So if I start at A, which has a pressure and a volume, and I go to B, and I go to C, and I come back to A. So if I go around the whole loop, I can see that my change in internal energy, so this is my internal energy at any point, but my change in internal energy is going to be 0 for a cyclic process. Okay, so that's internal energy, but what's work? Remember, work is pressure times volume. Remember, pressure times volume? So let's go and redraw this diagram and take each part individually. All right, so we started here at A, and we went to B. Okay, so this is P1, whatever pressure we, or P0, sometimes we like to do. And this is our pressure 1, or pressure 2, or whatever we want to call it. Okay, so when we go from A to B, do you see that our volume, if this is our original volume, V0, do you see our volume didn't change? If our volume doesn't change, did our gas expand or contract? No, it did not. So if there is no change in volume, if it's an isovolumetric process, then your work done is 0. And remember, delta U equaled Q minus W. So if this term is 0, then what your change in internal energy is just the heat that got added to the system. So we actually had to add heat to the system here to get more internal energy. Okay, heat shows up nowhere on the PV diagram. Heat, this heat here, is always found from using this equation. The U's can be found from the PV diagram, the work can be found from the PV diagram, but the heat itself has to be calculated. So you might want to write that down. This has to be calculated. But this, remember, 3/2 PV, so if we went, our change in U is going to be the 3/2 PV at point B, it's always final minus initial, minus our 3/2 PV at point A. And that would give us our internal energy, which in this case would also be our Q. So here our work is 0 because we had no change in volume. It didn't expand, it didn't contract, there was nothing we can do. So let's look at the next part of it. We go to C. All right, so here our work was 0, and we had a positive delta U, so we ended up with a positive Q. From B to C, let's color code this so that we can keep them all straight. When we go from B to C, remember, work is P delta V, or it's pressure times volume. And in this case, do you see that our pressure is constant? It stayed the same. So we can use this equation. That's one way. But do you see how when we take this pressure and we multiply by this change in volume, do you see we are finding this area? Do you see that? So work is also the area under the PV curve. Now in this case, from B to C, what did our gas do? Did it expand or did it contract? It got bigger, so if our gas gets bigger, do we have positive work or negative work? In this case, this is positive work. Okay? And we do have a change in internal energy because we changed our P and our V. So once we find this area, and if we were actually had numbers, we could find our delta U, then we could solve for our Q. We're not going to do that, but we could if we wanted to. So far, so good. So this is going to be a big important idea because we can use this even when it's not constant pressure. Because let's look at the third part of our problem. We went from A to B, in which case we had no work. We went from B to C, and there we had positive work, whatever this area came out to be, whatever, when we solved for this area, whatever it came out to be. And now we're going to go from C back to A. Now, is our gas getting bigger? Is our gas getting smaller? It's going from a big volume here to a smaller volume here. And so this has negative work. So we can use this cycle here as an idea. Okay, did it expand, did it contract, to see what the sign on our work would be. And that's really important. And remember that idea that we had, that it was the area under the curve. So that would be this area here. Okay, now that's kind of an odd shape, but do you see how we could split that up into a rectangle, and we can find that area, and a triangle, and we could find that area, and we put those two areas together, then we have the work done going from C to A. So this wasn't isovolumetric, it wasn't isobaric, so we could, we can't just P delta V it, because our pressure is changing and our volume's changing. But if we look at the curve, if we were to plot it out on a curve and we just found the area under that curve, then that would give us that amount of work. And then the total work, this is kind of cool. All right. So do you see we had this positive work that was the whole thing? The whole thing. And then we had the negative work, which was just this part right here. So the work from here all the way around is the area enclosed by the circle. So this is the total work done inside here is our total work done. So that actually, we don't actually have to solve A to B and B to C and then C to A and then add them all together. We could just find the area enclosed by a cycle, and that gives us the total work done. And you see that our positive work, which was the whole thing, is bigger than our negative work, which is this part going back down. So the total work here is going to be positive. The total amount of work done here is going to be positive. And remember we had that delta U equals Q minus W? So if this number is positive, and remember this number is 0, because we got back to the same place we started, so our change in U for the whole cycle was 0, then this Q has to be positive too. What's it mean when your Q is positive? That means you have heat added to the system. So this had to be powered by maybe a coal fire or something like that. You needed to somehow add heat to the system to get this system to work. How's that looking? So the important thing about PV diagrams is you're looking at the area under the curve. And in this case here, our delta U is going to our delta U is 0. So if we rearrange this, our Q is equal to the work done. So the amount of heat added has to equal the work done in order to have a delta U of 0. I wouldn't go around memorizing these things, but what I would do is I would memorize these big ideas. If I go into a cyclic process, if I come back to where I started, then my change in energy is 0. Or if it's isothermal, your change in energy is also 0. This is not isothermal, because isothermal is for a single process, not for a cycle. Okay, but if you had an isotherm on a PV diagram, looks like the 1 over x graph, so it kind of looks like that. And that's tricky to find the area under that. We have to use calculus for that, and we're not going to do that, so don't worry about finding the work isothermally. Okay? If you have any questions, please let me know, and I will see you tomorrow. Thank you. Bye-bye.